minutes early for the 9 a.m. Early morning session. So it's actually, I would say, all of our great privilege and honor to have Rob Schapire here giving the first talk of the day. And this is another freebie intro for me, because not only do I not have to try to remember anything or even think about what to say, if I forget 99% of what there is to say, there's still a lot to say. There's still enough to say. So for instance, a lot of people know that Rob came up with boosting, and they don't even know that he came up with the first boosting algorithm as the solution to open problems. So we just forget that he did that. Then he's
nobody forgets that.
For all the live stream viewers that did not hear the ruckus in the room, I just got denied my accuracy, but for those on YouTube. Of course, so Rob Schapire won the Gödel Prize for, Rob Schapire and Yoav Freund together won the Gödel Prize for AdaBoost. And it's important to note that this was the first Gödel Prize awarded to machine learning. So the very unfortunate non-machine learning researchers such as Shafi Goldwasser and Sanjeev Arora felt completely forced to switch into machine learning. They were the previous recipients. Other things that Rob is known for that, again, we could just remove boosting and we'd still have reasons to invite him for every talk ever. He, after graduating from PhD, he went to Bell Labs and had central contributions to online learning. One of my favorite papers from that era is the kernel perceptron paper he wrote together with Yoav Freund. And actually the AdaBoost algorithm is based on their hedge algorithm. So I could keep going on. There's like a whole era of nice algorithms for online learning from him and Yoav from that time. And the other interesting thing is that if I removed all of his academic results, I would still feel compelled to introduce Rob, because he's maybe the most, one of the most dedicated mathematicians I've ever met. He still just wakes up every day and churns out some tech and some theorems just every single day. And even if we removed that, I would still feel that we'd have 45 minutes to talk about, because he might be the nicest person I've ever met. So I think I should stop there, even though I forgot 99% of the nice contributions to say about him, and take it away.
Thanks, Matus. Very nice introduction, to say the least. Right, so I'm going to talk about convex analysis at infinity and an introduction to astral space, which I'll say what it is. And this is joint with Matus and with Mira Dudik. And if you want to do more reading, here's a link. Okay, so this talk actually is about convex functions, and in particular, how to minimize convex functions. And minimizing convex functions, I'm sure everybody knows, is the basis of lots of machine learning and statistical algorithms. I've listed a bunch: maximum likelihood, maximum entropy, logistic regression, boosting, support vector machines. The list goes on and on. So I might as well, on the very first slide, warn you that this talk has very little actual learning in it. It's really about convex functions, but the connection to learning is this. So this is going to be almost all the learning in the talk. So convex functions are just really, really nice mathematical objects. They have lots of nice properties. So like a local minimum of a convex function is always a global minimum. And if the gradient is 0, then it's global minimum. And it's just usually easier to find algorithms and analyze algorithms for minimizing these functions. I mean, look at that. How hard can that be to minimize that function, right? And they just have beautiful properties. So usually when we think about minimizing convex functions, or it's common anyway, to assume that the function actually attains its minimum at some finite point, like this one does. But of course, that's not always true for convex functions. So this is the exponential function, which is a super simple convex function, but it has no finite minimizer. There's no finite point that minimizes that function. So instead, if we want to think about minimizing it, we have to minimize it with a sequence, as that sequence heads off to infinity. In this case, heads off to negative infinity. And this comes up in cases of practical interest. So for something like boosting, even logistic regression, it's not just a corner case, it's often the typical case. And when you want to, it's still possible to prove convergence, but it's just more challenging in these cases. And usually what people have done in the past is to come up with techniques that are rather highly tailored rather than more general, the kind of general techniques you can use when you have a finite minimizer. So what we're trying to do here is we're trying to develop a theory for studying those minimizers at infinity. So let me talk again about the exponential function to make this more concrete. So here's the exponential function, e to the x. I already said there's no finite point that attains its minimum. So instead, it can be minimized by any sequence of points that head to negative infinity. And so naturally, we wish we could say that this function is minimized at negative infinity. That would be a natural thing to say. And mathematically, there's a way we can do that. What we can do is we can take the real numbers and we can just extend them by adding plus infinity and negative infinity. So these are called the extended reals. I'll write them as R bar. So it's just the reals with plus and minus infinity. And then after we've extended the real numbers, we can take the function itself and extend it in the natural way to the extended reals, where we just let the function be equal to 0 at negative infinity and plus infinity at plus infinity. Very natural, simple, almost obvious. And this extended function has some nice properties. So it's continuous over the extended reals. Whereas the original function did not attain its minimum, this one does attain its minimum at negative infinity. And the function kind of feels convex. We don't really have a way of defining convexity when you're working over the extended reals, but it kind of feels convex. And it feels also like we could maybe extend the derivative so that the derivative at negative infinity would be 0, and then you would still have this property that the minimizers occur where the gradient is 0. So when you're working in one dimension like this, everything seems fairly clear how to add these points at infinity and how to extend functions to this enlarged space. But things become much more interesting when you go to 2 or more dimensions. When you're in 2 or more dimensions, it's much less obvious how to do this. Yeah.
Where I might want to do this, like why would be dissatisfied with like the maximum float value? What would go wrong if I just clipped things there?
The maximum what value?
Float, like the biggest number, the
Oh.
negative number my computer can represent.
Well, let me keep going, okay? And let's look at some examples later. And okay. So in 1 dimension, sure, that's fine. But in 2 dimension, it's going to be much more interesting. Okay, so what we're trying to do is we're trying to take n-dimensional Euclidean space, Rn, and extend it to include points at infinity. And our aim is to try to reveal the structure of how these functions behave at infinity. What we're trying to do is we're trying to build up foundations. Okay, so convex optimization is built on this very strong foundation of convex analysis. And we're trying to do the same thing. We're trying to build up foundations to make it easier, more straightforward to do things like to prove convergence of algorithms. And we're hoping to make the study of convex functions more complete and regular. For instance, so that every convex function, when we extend it to the new space, will have a minimizer. And we're trying to do this in a way that's compatible with all the key ideas of convex analysis. So there's kind of an analogy to think about what we're trying to do if you think about just numbers. So imagine you're living in the time of the ancient Greeks and all you know about are the rational numbers. So you only have the rational numbers. And then you want to figure out what the length is of the diagonal of a unit square, a 1x1 square. And of course, you have a problem because there is no rational number that's equal to that diagonal, the length of that diagonal. Today, we know that it's square root of 2, and we know that it's not rational. But then that was a problem. Well, what you could do instead, and the Greeks actually did this, is you could approach that number using sequences of rational numbers. So here are two different sequences that both converge to square root of 2. The first one was actually known to the ancient Greeks. The second one is just based on the decimal representation. And so the point is that in these terms, you don't really need the real numbers, right? You could just do everything you ever wanted to do with real numbers using sequences of rational numbers, at least in principle. But of course, you know, we know today that that's a terrible idea, that it's much more preferable to take the rational numbers and to extend them to the real numbers, because the real numbers are much more complete and regular and well structured. So, yeah. Yeah, that's true. Yeah, exactly. I mean, that's one way of doing it. Yeah, to define equivalences of, yeah. But you're still what you're doing is you're creating a mathematical object, and you're working with that as an object in its own right, as opposed to constantly going back and dealing with sequences. So that's what we're doing today. When we want to think about the minimizers of convex functions at infinity, we're dealing with sequences. And so we could continue doing that in the same way. But maybe what we're saying is that maybe it would be nicer to study those minimizers at infinity as mathematical objects in their own right. And what we're hoping is that this larger space will be more complete and regular and so on. So that's the hope. Okay, so what I'm going to talk about, so what we're doing in this work is we're introducing this larger space called astral space, which is an extension or an enlargement of Euclidean space that includes points at infinity. And then what we do is we show how to take functions defined on Rn and extend them to this larger space, astral space. And we're doing it in a way where we're also studying many key properties and topics, especially how they extend to astral space, especially things from convex analysis. So here's an outline of what I'll talk about. I'll talk about what these minimizers at infinity can look like and how to construct astral space and what points in the space look like and how to extend functions to astral space. And hopefully I'll have time to talk about convergence of iterative algorithms at the end. Okay, so before we dive in, just a very quick slide on notation. So first of all, I'm always using n for the dimension of the space we're working in. So we're working in Rn. And scalars, I write in italics like this. So points in R are written like that, not in bold. And vectors, so points in Rn are written in bold like this. And so for instance, a tuple, which is a vector, x, has components. So the vector is in bold, but the components are not in bold in x1 through xn. So you can tell the type by looking at the font. And all sequences are always indexed by the letter t. So t is always the index of all sequences. So limits and convergence always are with respect to t, are always as t goes to infinity. And I write sequences like this in parentheses. xt is the sequence x1, x2, and so on. Okay, so hopefully this is all the notation you need. Okay, so what can these minimizers at infinity look like? So we're imagining we're given a convex function f, which is defined on Rn, Euclidean space, and its range is R bar, so real numbers and plus minus infinity. And if it's got no finite minimizer, as we've said, it can only be minimized by a sequence. So what can those minimizers at infinity look like? So in one dimension, as we've said already, the only possibilities are plus minus infinity, not very interesting. So in two or more dimensions, there are lots more possibilities. So let's look at some examples. So here's one example. So this is in R2, function defined on two variables, x1 and x2. And so algebraically, this is what the function is. And here I've plotted, or actually Matus did this beautiful figure. So Matus plotted the the surface of the function on the top part. So you can see it's like the back end of a canoe, this particular function going off to infinity. And in the bottom part is a contour plot. So each one of these curves is showing the set of points where the function has a particular value. So it's like a topographic map showing hills and valleys and so on. Sometimes more helpful. Okay, so how would you minimize this function? Well, to minimize the first term, we need x1 to go to infinity so that that term is going to 0. So for the first term, we need x1 to go to plus infinity. And for the second term, we need x2 minus x1, this difference, to be going to 0. So we really need x2 to be going to infinity at the same rate as x1. So both of them have to go to infinity, but they have to be going at the same rate. So for instance, you could let x1 and x2 be equal to t, and then just let t go to infinity. So you're getting a sequence like 1, 1, 2, 2, 3, 3, and so on. And that does indeed minimize this function. So you're heading off in a straight line along a ray. So the point is that it really matters how the sequence goes to infinity. And for instance, the direction matters. So if you go in a different direction, you won't be minimizing this sequence, this function. And offset also matters. If you take that same sequence and you move it over by a fixed amount, you also will not be minimizing this function. Okay, so this is to try to answer your question. This is why it's not enough to just cap things at plus minus infinity. You really have much more interesting things happening. Okay, so this might make you wonder, well, for a convex function, can you always minimize it along a straight line, along a ray? So can every function be minimized, convex function be minimized along a ray? And the answer is no. So here's a different example. This function is also convex. And again, I plotted it up here. So to minimize this function, well, to minimize the first term, we again need x1 to be going to infinity. To minimize the second term, x1 is going to infinity, so x1 squared is going to positive infinity. And so to minimize this, we need x2 to be going to infinity, but it has to be going to infinity much faster than x1 so that this exponent will be going to negative infinity. So it basically has to be going at least quadratically faster. So for instance, this sequence, t squared along this parabola will minimize this function. And it's possible to show that this function cannot be minimized along any straight ray. Yeah?
Functions that are lower bounded. So like for example, in the 1D case, we have like y equals x. Would we say it's minimized as x goes to negative infinity at negative?
Y equals, so the function is equal to x? Is that what you mean by?
Yeah.
Yeah, so their x is being minimized at negative infinity. Yeah. So it's yeah. I mean, the same thing works if it's not lower bounded.
Okay.
Yeah. Okay. Yeah.
If it's not lower bounded, you'd say that anything that goes to negative infinity is a minimizer?
No. Just in the example he said. Okay. No. The same type of issues can come up also. I'm not sure I can think of an example off the top of my head.
What would be the sequence of minimizers? I mean, I'm not sure, like, if it's not lower bounded. I mean, compare between different sequences that both go within.
Well, any sequence where the function values are going to negative infinity would minimize the function.
Okay, so anything goes to negative infinity minimizers. Okay.
Anything where the function values are going to negative infinity. Yes. Okay, so I'm not sure, like you maybe can just take log of this. I don't know. I can't think of an example off the top of my head, but the same issues are going to come up there. So nothing really changes if it's not lower bounded. Yeah. Okay. So it seems like there are interesting sequences to minimize convex functions. How can we capture them? That brings me to the next part of the talk, which is how to construct astral space. So these sequences heading off to infinity don't converge because there's nothing out there for them to converge to. There's just nothing out there. So if we want them to converge, there's a simple idea, which is to just add new points to Rn, to Euclidean space, that can become the limits of those sequences. And you can do this in math. You can just invent stuff or construct stuff. And so that's what we're going to do. We're just going to add these new points that we construct, which will become the limits of those sequences. But to do that, there are two key questions that we have to answer. First of all, which sequences should have limits in this space? And secondly, when should two sequences have the same limit? When should they have the same limit? And if you can answer both those questions, then we can construct the space, because we just add new points to be the limits of all the sequences that are supposed to have limits. And we do it in such a way that if two sequences are supposed to have the same limit, then they actually do. So in other words, we're just adding a new point to be the limit of every group of sequences that are all supposed to have the same limit. Okay, so we're going to focus on those two key questions. So let's look at some examples to try to get some intuition. So again, the first question was, which sequences should have limits? So I won't give a full answer, but if we just think about a sequence that's following a ray off to infinity, oh, it kind of wiped out my axes. I don't know why I did that. Anyway, there are axes barely visible here. Oh, okay. Okay, yeah, anyway, it's a sequence following a ray, a straight line off to infinity. And so it's reasonable. It's like the simplest way of going to infinity. So surely a sequence like that should have a limit. Okay, so I've drawn it pictorially here, and here's the algebra if you're interested in algebra. Okay, so which sequences should have the same limit as this particular sequence? Well, if you just follow the exact same ray, but you do it at a different rate, like you do it at a faster or slower rate, then of course that should have the same limit. That's kind of clear. But here's a less obvious question. So here's our original sequence. And suppose we take it and we shift it by a fixed amount, by a fixed offset, to get a new sequence, the cyan sequence over here. Well, that's also following a straight line, so it should have a limit. But should those two sequences have the same limit? Do we think they should have the same limit? We really can answer this question either way because you're doing a construction. But we believe that the answer should be no for this, because we've already seen that offset matters for minimization in one of those examples. And because in the applications we're thinking about to machine learning and statistics, we often really do care about offsets. We don't only care about the direction of minimization. We often also care about that offset. Okay, so how can we capture these intuitions? So there's a basic principle that we adopt in this work. The basic principle is to focus on the limits in every direction along every one-dimensional projection of the sequence. So let me, rather than trying to explain that, let me show you with an example, coming back to this example. So here are the sequences as before. And we want to decide if they should have the same limit or not. So what we do is we pick a direction U, and we consider the projections of those sequences in that direction. So let's say we pick this direction, 1, 0, which is straight out to the right. And so we project along the line that goes through that vector U. And we take the first sequence, the black sequence, and we just project down onto that line. And you can see pictorially that that sequence is going off to positive infinity. And you can see it algebraically also because that projection really is just taking an inner product of each of the elements xt with the vector u, and that's going to positive infinity. And then we do the same thing with the other sequence, the cyan sequence. And again, we see that it's going off to positive infinity, but either graphically or algebraically. So far, these sequences are behaving the same on all of the vectors u we've considered. But we're supposed to consider all of them, all possible vectors u. So let's look at another one. So here's a different vector u. And now if we take the black sequence and we project onto this direction rather, then what we see is all of the points project down onto this single point. And algebraically, those inner products are equal to 0, and so they're just converging to 0. Whereas on the other sequence, if we take the other sequence and project down in the same direction, then we're getting a different point, a different value, which happens to be 5 in this example, and which is converging to 5. And so they have different limits if we take the sequences and project them in this direction. So yes?
Just define equivalence on sequences, saying that two sequences are equivalent if for any convex function. Say, yes.
Okay, you could do it for any convex function. What we're doing is not any convex function, but we're doing any projection u. So we're doing the same thing, but not for convex functions, but for linear functions.
And then you will say that.
So what you're talking about, yeah, go ahead.
Sorry, and then you would say that, maybe I'm writing ahead, but you would say this is equivalent.
Yes. Yep. Okay, so in this example, we found some direction where the sequences have different limits. So therefore, these two sequences need to have different limits. Okay, so to pull this together, which sequences should have limits? Well, exactly those that the phrase we use is to converge in all directions, meaning that this limit, the limit of these one-dimensional projections, exists for every possible direction u. So those are exactly the sequences that will have limits. And when should two sequences have the same limit? Well, exactly when they are all directions equivalent is the phrase that we use, which means that they have the same limit in every direction. So if you take the two sequences and you look at these one-dimensional projections, those limits have to exist and they have to be equal to each other for every possible direction u. And if that's the case, then they have to have the same limit. And note that these limits could be positive or negative infinity. We allow that. Right? So once we make those decisions about which sequences have limits and when are the limits the same, then we can take Euclidean space and expand it according to those criteria in the way that I discussed before. And the space that you end up with when you add all these points at infinity is called astral space. And the notation we use is this. So it's Rn with a bar over the whole thing. Not R bar raised to the end, it's Rn with a bar over the whole thing. Okay, so that's what astral space is. So in one dimension, all we're doing is adding plus minus infinity if you think about it. So one-dimensional astral space is just the same as the extended reals. Other questions at this point?
Who came up with the name?
I think it was my idea. So there's another space called cosmic space that was done by Rockefeller and Betts. And so it's somewhat of a tribute to that. But then we're also thinking about stars. You know, astral refers to stars, and stars are figuratively, not literally, but figuratively, these points off at infinity. Okay, so some topological properties of astral space. So the first thing is that astral space is compact. So if you know what compactness is, great. If you don't, I don't have time to explain it, but it's just this very powerful mathematical property that is really useful for things like proving convergence of iterative algorithms. That's really what makes it so hard to prove convergence of algorithms operating on Rn, is that the space is not compact. The other property is that every linear function can be extended continuously to astral space. And I'll say a little bit more about what that means in a few slides. But what follows from that is that anything linear, in quotes, is likely to behave nicely when you extend it to astral space. And that's especially important in convex analysis. So it means we can generalize things like linear maps and hyperplanes and half spaces, which are all clearly linear. But then things like convexity, convex sets, convex functions, those are also, if you think about the definitions, also based on linear stuff. And same with things like conjugates and gradients. So all these things generalize to astral space. And let me also mention that astral space is not a vector space, and it's not even it's not a vector space, and it's not even a metric space. So you have to think differently because you're working in a space that's not a metric space. But it nevertheless has many, many other nice properties. Yeah. There's no metric. It's not metrizable. Yeah. Okay. So what are points in this space like? What are they like? Well, as I've said already, the simplest sequence going to infinity is a long array starting at the origin. If you could see these axes, you would see that this is the origin heading off to infinity in a particular direction, v. So this sequence converges in all directions, yeah?
So you might keep getting back to that later, but I'm a bit confused how to reconcile this with the example before, because if you look at sequences form t and t to the power of r, then it seems that all of them are equivalent for any like r greater than 1.
Oh,
but
yeah, they all lead to the same point. Is that what?
Before tell us that you need that some of them would minimize your function and some wouldn't?
Yeah, let me get to that.
Okay.
Let me get ask that. If I don't get to it, ask again later after I've covered a little more. Yeah.
It's just a property question. Is astral space itself a convex set?
Yes, but I haven't. I'm not going to define convexity in this time. I mean, you have to say what it means to have convexity, but
Right.
Yeah. But yeah. Yeah, I'm not going to get to that in this. Yeah. Okay, so this sequence converges in all directions. It's not that hard to prove. So that means it has to have a limit in astral space. And that limit of this particular sequence is called an astron. So a point in astral space is just called an astral point. An astron is a particular kind of astral point that you get, again, by picking a direction v and heading off to infinity in that direction. And it's written like this, omega v. So omega is like positive infinity. So it's kind of like you're taking a positive infinity and multiplying it by v. Okay? So that's what an astron is. And astrons are really important because they turn out to be the building blocks of all astral points in a way that I'll explain in a minute. Okay, so that's what astrons are. So let's look at a more interesting example. So let's say we pick 3 vectors, v1, v2, and q. And then we form a sequence where we just do t squared times v1 plus t times v2 plus q. So you're basically, it's like you're starting at q and you're following this parabola off to infinity. So intuitively, this sequence is converging to infinity most strongly in the direction of v1. But then you get this secondary kind of convergence to infinity in the direction of v2. And q is acting as like a fixed offset. Okay, so you can show that this sequence converges in all directions. So it has to have an astral limit. By the way, I'm writing astral points in bold with a bar over them, so you can tell the type again. So that's an astral point. It turns out that we can write this limit in a particular form. So we can write it like this. So astrons we've already seen. So omega v1 and omega v2 appear here. Those are the astrons associated with v1 and v2. And then q appears by itself. And then we have this funny plus sign. So if you can see it, it's a plus sign with a dot on the left end of it. And this is called leftward addition. So it's like vector addition in certain ways, but not in every way. It doesn't have all the properties. In particular, it's not commutative. And I'm sorry, I don't have time to define it. It's not that hard a definition. I just don't have time. But it's not commutative, and it gives a kind of, its definition gives a kind of dominance to the term on the left, which is why it's called leftward addition. And that dominance to the term on the left is corresponding to the fact that you have this ordering of directions in which this sequence is converging to infinity, that it's going to infinity faster in the direction of v1 than v2. So it turns out in general that every astral point can be written in this form as a leftward sum of astrons together with a finite part. And what's more, if we want to, we can choose these vectors v1 through vk to be orthonormal, and we can choose q to be orthogonal to all the vi's. So every point can be written in this form. Yeah? Yes.
So then it's not intuitive to me that this is commutative, because addition in the space of sequences is commutative, right?
It's, well, I mean, just think about these original sequences that, you know, the sequence you're constructing is going to v1 much faster than v2. And so that's not a commutative operation. If you reverse those, you'll get something quite different. And so that's reflected down here in the fact that v1 appears on the left of v2, and that's because it's dominant to v.
The indexing here is kind of a coincidence in some sense, right? We could have indexed, like how I write the leftward addition is determined by the speed of convergence, not by the order of the terms I wrote.
Well, they're the same. They correspond to each other. So the order of the terms is the order of the terms down here is corresponding to the fact that you're going to infinity much faster in the direction of v1 than v2. So you could, you know, reverse these tv2 plus t squared v1, but you would still get the same thing down here. Okay. Yeah.
So if we had a different, like if we had t log t or t to the 1 plus epsilon, is that going to be the same x bar?
Yes, it is. And so, yes, so it's not, so this is not sensitive to the fact that this is just an example. It's not sensitive to the fact that, you know, it's t squared and t. It's sensitive only to the fact that t squared is going to infinity faster than t. Yeah, good point. Yeah?
Or you said you look at all one-dimensional projections, right, of the sequence, and then you say they have the same limit if they have the same limits on all one-dimensional.
Right.
So if we just pick a basis for RD and look at projections onto the species, can they just look at the limits and this?
You can't just look at the, no, yeah, you'll get something different. You'll get something different. It's not, and you'll lose much more information if you do that. So you have to be considering all possible directions. Yeah. Okay. Yeah. Okay. So every point can be written in this form, and this number k, which is the number of astrons we used here, is called the astral rank of the point x bar. So the number of astrons you need to represent that point. So if astral rank is 0, then you have no astrons, so you just have a point in Rn. So the points with astral rank 0 are exactly the points in Rn, which is a subset of astral space. And if the astral rank is 1, that means that you reach that point by following a straight line. Okay. Let me talk about extending functions to astral space. Okay. Okay, so let's say we're given a function f, and we want to extend it to astral space. So this function is defined on Rn. We want to extend it to a function defined on astral space. And the extended function we write as f bar to distinguish it from the original function. So how should we define it? Well, if we go back to the exponential function that I had before, we want to define an extension for this function f, which is f bar. And we already said that the natural way of defining that extension f bar at negative infinity is to be 0. Why? Because every sequence of points going to a negative infinity, on every such sequence, the function values are going to 0. So that's really the only natural way of defining the extension f bar at negative infinity. And same thing at plus infinity. So it's the only way of defining it, extending that function to the extended reals. So we can use that idea in general. So in general, we're given a function f, want to define its extension. So let's say we're given a point x bar. We want to define that extension at the point x bar. What should we do? Well, let's suppose we're in a nice case where the limit of the function values exist and are all the same on every sequence that converges to that point x bar. So this is exactly what we saw for the exponential function on the last slide. That's exactly what was happening there. So in that case, the only reasonable way of defining the extension f bar at that point x bar is to be that limit of those function values, which we're assuming in this case is the same for every such sequence converging to x bar. And if we can do that for every point x bar, then this extension f bar becomes the only possible continuous extension of the function f to astral space. Okay, so for instance, for linear functions, like this one, for linear functions, if you work out what that limit is, the limit of those function values are just the limits of these inner products, which you might remember we constructed the space in such a way that that limit would be the same for every sequence converging to x bar. We really set up the space so that would have that property. So therefore, this function has a continuous extension. And the upshot is that, as I said earlier, every linear function can be continuously extended to astral space. Yeah, question.
Can you explain what does continuity mean here? Because normally we define continuity in terms of epsilon delta. We said it's not rechargeable.
Yeah, well,
with your topological notion of continuity.
Right. So we have to define a topology, which I've glossed over. I may have been acting like I defined the topology, even though I didn't. But we can define a topology. Let me not. Yeah, because I have extra slides. So if you want, I can put that up.
Excuse me.
Yeah.
Isn't this analogous, so much more structured than the Orison compactification, which I believe is such that it makes extends every continuous function.
Or the stone check, or it's called Orison.
It's stone.
Yeah, so it's exactly analogous to stone check. That's right. Yeah.
I remember it from my topology.
Yes. Yep. So stone check does every continuous function. We're doing every linear function, which has, and it's been studied in general, not just linear functions, continuous functions, but general compactifications. So that idea is not new. But yeah. So what we're doing is to take a known compactification and really studying it to death. Okay, so coming back to this example, So it's possible in this case to show that the function extends continuously to two-dimensional astral space. Maybe I should gloss over this. Okay, and we can say exactly what the limit is here. Let me move on since I'm short on time. So if the function f does not have a continuous extension, we still can do things. It's not like all is lost at all. Our theory extends even if it does not have a continuous extension. So in the continuous case, we define this extension to be the limit of these function values, which are the same for all sequences. In the general case, these limits, you might get different limits of the function values for different sequences converging to the same point x bar. So of all those, we take the minimum possible value of that limit. Yeah? Did you have a question? Oh.
Well, I mean, that doesn't answer my question from before.
Oh, what was the question again?
The problem is that since this might happen, right? If you wanted to show us this example with you have to take x1 and x2 in a particular way to infinity. I don't see how this doesn't allow you to express the way in which you have to take right.
Okay, so what it shows is actually I'm going to talk about that example on the next slide. So okay, so some properties of this definition is that this extension must always attain a minimizer in astral space. So the original function might have not have a minimizer, but its extension always does have a minimizer. And what we can say is that if this point x bar minimizes f bar, that holds true if and only if there's some sequence that minimizes the function f. Okay, so that's what happens in that example. So the minimum, let me actually go into it. So here's that function for the second case. And so we said it could be minimized by this sequence, which we can write in this form using standard basis vectors. And we know that a sequence like this converges to a sum of two astrons, leftward sum of two astrons. And so f bar is minimized by this point x bar. So it's not minimized by every sequence, but there exists a sequence that minimizes it. You look so unsatisfied.
It has to go to infinity, but not everything goes to infinity minimized. So you want to actually understand what minimizes. Here it seems you're not solving it. You're still saying, well, some of these things minimize, some others don't. We don't actually have.
Yeah. So when you don't have continuity, that's true. Yeah. So when you don't have continuity, all you can say is that there exists a sequence that minimizes it. When you do have continuity, so if the function is minimized at this point x bar, then you can say every sequence converging to x bar minimizes the function. Okay. Okay. Let me move on. Even though you don't look happy. Okay. Right. Okay. So I didn't have time to talk about the last part. So yeah. All right. Yeah, I guess I better stop. That's.
I'll ask you a relevant question.
So let me just give the upshot of the. So it's possible to show that there are sequences where the gradient converges to 0, but where the function does not converge to the minimum. But it turns out that this weird behavior goes away if you also know that the function, the extended version of the function at the point you're converging to is continuous. So if you add an astral continuity assumption, then this weird behavior goes away. So that fact allows us to prove the convergence of a whole bunch of standard iterative methods applied to a whole bunch of machine learning problems, statistics problems, like logistic regression and boosting. For these problems, all of these have continuous extensions. So you're always in the continuous case with these. Okay, sorry I went so much over. So I'll just stop there. If you want to do more reading, this is going to be published as a book, but there's a draft version on archive. It's over 500 pages. Don't freak out. But it's got a short, reasonably short intro. So you can read the intro, get a taste for it.
We have a literal fireside chat now. And we are having time.
Do I take one question?
So, yeah, well, go ahead.
Yeah.
This gives me the projective space. This has R and plus one mod on R star. But is this astral space also like a higher dimensional space module?
Is it also a what?
Is it also like a higher dimensional space like R and plus K mod also?
Let's see. I'm not sure I followed everything. Okay, so there are many ways of compactifying Rn. And one way is a one-point compactification. Is that what you were saying?
Yeah, I wonder like how I should be entering this compactification as the astral space. Like from projective space, this is Rn plus one mod on R. And is this also a higher dimensional space mod also?
I don't know. I don't know the answer to that. I haven't thought about that. But the space has this interesting geometry. I'm not sure if this would quite answer your question, but it's got this interesting geometry that in the center you have Rn, and then if you were kind of to take a spaceship and head off in a straight line direction, you would, if you travel infinitely far, you'll reach an astron. And that astron is the center of its own piece of the space. It's called a galaxy that is one dimension lower. So it's n-1 dimensional. And then you can do that again. So once you're in that n-1 dimensional space, you can pick another direction, head off in that direction. You'll end up at an astron in that smaller space, and it's at the middle of a space that's n-2 dimensions. So every time the number of dimensions goes down. So it's kind of like, it's sort of like if you just think of a polytope, like if you think of like a cube in 3 dimensions, in the middle you have a 3-dimensional part, and then you have these 2-dimensional faces and 1-dimensional edges and points. So it's kind of like that, except for the fact that you have a different face in every possible direction, and the faces never actually meet the way they would in a polytope. But it's kind of analogous to what's happening there. So that's probably not answering your question at all, but hopefully it gives you a sense of what this space is like. You want to cut it off or take questions?
Well, the schedule says fireside chat, so I'll ask Rob some general questions from like that, and then people that want to ask, we'll have time for general audience questions. So if you want to ask a question about astral space, you can do so. And also ask questions about not astral space.
Yay.